Good evening. Welcome with us today, LSE Professor Martin Anthony and Joe Borch, a resident lecturer at St. Martin's Institute. Joe Borch is head of mathematics group at St. Martin's, also teaching investment management, managerial economics and statistics. Professor Martin Anthony is with us, has been giving a few lectures to our students. We'll be giving another lecture this evening, and has agreed to have an interview by Aspire magazine for our readers. Thank you so much, Professor Martin. Professor Anthony, you have been at LSE for over 20 years now, right?
Yes, 23 years.
23 years, to be exact.
Yeah.
Could you give our readers an account of your experience at this prestigious university, and what originally led you to this career choice?
Okay, so I've been at LSE, as you say, for 23 years, but I started while I was still finishing my PhD. In fact, I was a PhD student at Royal Holloway College for 2 years, and then I was hired to a lectureship at LSE. I finished my PhD my first year there, and then I have been there ever since, so it's actually the only job I've ever had. And when I was a PhD student, I was teaching a little bit at LSE, just some tutorial classes. And so I've worked my way up the ladder at LSE from graduate student to professor now. And although it's 23 years in the same institution, the job has never been the same, it's always different. As time's gone on, I've taught different courses, done different research, taken on new responsibilities all the time, so it's been quite varied and interesting. And one of the most interesting aspects of it is actually getting involved in collaborations like this. So it's just taking me to interesting places in the world.
I can imagine. Which is the most interesting?
Well, the most sort of exotic sounding is probably Kazakhstan. I go there 2 or 3 times a year.
Definitely so.
Yeah.
So I can imagine. In your entire career, you have been involved in some partial or wholly produced publications. Could you give us a brief overview of these particular publications?
Of my publications? So I've really published sort of, I guess, 3 different types of things. A couple of textbooks for first and second year undergraduate students. Then research papers and monographs connected with my academic research, which is on the mathematical underpinning of machine learning and artificial intelligence. So it crosses into theoretical computer science, really. And then the other sort of things I've produced are a number of subject guides to help students on international programs get to grips with their subjects.
Interesting, very interesting. And as you said, I have Mr. Joe Borch here as the lecturer, and the topic for tonight's discussion is the monster that is mathematics. Joe.
Okay, going on the question that Joe asked, can you just tell us a little bit of your current interest research you're doing?
Yes, so I'm interested in how we can prove things mathematically about methods for extracting meaning and data from large sets of data. So this is connected with machine learning, where we want to automate the process of looking at massive data sets and learning something from them. This is an old subject. It goes way back to sort of pattern classification methods of the 1950s, 1960s. And now it's even more important because of the huge data sets that people have to grapple with, and which are now available because of increased computing power. So behind the methods for analysing big sets of data are techniques from statistics and mathematics, and that's where my research comes in. It's looking at questions of how can we take a large set of data, classified data. So imagine, for instance, just to give you a concrete example of a machine learning problem, imagine you're trying to classify email messages into legitimate email messages and spam or junk email messages, and that you've got a computer system that's trying to learn from the user what he or she considers to be spam and what they don't consider to be spam. So rather than the machine having an a priori classification of what junk mail is, it will learn from the user as the user clicks buttons on receipt of emails and says, this is junk. So that it will begin to recognize what the user considers to be junk email. And that's a sort of learning process that we want to automate. My specific concern in my research is how much data do we need before we can be sure that the machine has got it almost right. So another example is fingerprint recognition, which is a feature on the new iPhone 5S, for example. How many times does the iPhone 5S need to see your fingerprint presented in different ways before you can be sure that that's enough and that thereafter it's going to work most of the time. Of course, it doesn't always work, but we want it to work most of the time. So it's about pattern recognition, learning from data.
So you've taken a monster and now you are taking your way forward.
Yes, I'm taking a monster that is the evil artificial intelligence. It's going to take over the world, make everybody redundant and know everything about everybody. Yes.
But underlying all this, there's the history of mathematics. The history of mathematics is the same thing. People 2,000 years ago, 3,000 years ago, ask different questions. Could you just comment on that and expand a bit on looking at patterns?
Well, looking at patterns is essentially what mathematics is about. Not just looking at patterns in modern data sets, which is where my own interests come in, but patterns in numbers has long been the primary sort of driver for pure mathematical research. Then patterns in structures, which led to group theory and other algebraic structures. Patterns have really always been the driving force in mathematical research. People want to try to describe precisely symmetries and patterns that they see in structures, or whether they're abstract mathematical structures or real geometrical physical structures. It's been a primary driver of a lot of mathematical research. People think maths is just about trying to do calculation and deal with numbers, but it's not. It's about trying to make sense and tidy up the world around us and theorize it in a nice way that captures symmetries, patterns, and logic.
Which brings up two further questions. One, the difference between pure mathematicians and applied mathematicians. And the second one is the perception to students and the general public about mathematics. Can you comment on that?
I think sometimes this binary divide between pure and applied mathematicians is artificial and slightly blurred. Although you might think that people who draw their problems from applications and then study them mathematically should be classified as applied mathematicians. I think that's just a crude classification. They may be drawing the problems from applied domains, such as in my own case from computer science. Computer science raises a number of interesting mathematical problems, which we then look at using mathematics. And to be honest, a lot of the people who are doing that sort of work are pure mathematicians deep down and wouldn't actually be interested in the problems if they weren't interesting purely from a mathematical perspective. So I think there are certainly those in sort of physical applied mathematics whose ultimate aim is to model physical phenomena, but there are other people working in the sorts of areas I'm working on, theoretical computer science, who deep down are still pure mathematicians. They're trying to find mathematical beauty in problems that arise from physical situations in computer science. So I don't think the distinction is as simple as people think. We have, in my department, we have an MSc in applicable mathematics, which is a sort of halfway house between applied mathematics and pure mathematics. That's why we call it applicable. It's a sort of maths that would be useful in applications, but the focus is not so much on the applications. I think even so-called pure mathematicians are often ending up doing applied research because they're taking the mathematics that they're working on and applying it to other areas of mathematics. That's a sort of applied mathematics in a way. They're solving other problems in other areas of mathematics using techniques that they've discovered in their own area.
So it's a different era from 200 years ago?
Yes.
Where the pure mathematicians didn't really care about the application, they just were happy doing the monster thing?
Yeah, well, and to be honest, I don't think in this world we can any longer easily get away with simply saying, I'm doing pure mathematics for the sake of it because I love it and I enjoy it. Increasingly, governments, funding agencies, universities themselves are saying to people, we've got to try to convince our bosses, the public, the government, that somehow your research is having what they call impact. And by impact, they mean impact in the real world. I think there's a slightly dangerous emphasis on that at the moment in the United Kingdom anyway, where research funding has to show some economic benefit or at least some potential economic benefit, and where the research of universities is assessed not just by the quality of the papers published, but to a lesser but significant extent by the impact of the research, where impact is defined, really in terms of its economic impact upon, the development of new products in industry and so on. So I think it's a slightly uncomfortable position that a subject like pure maths occupies at the moment.
If we leave that to the politicians and
I wish we could.
stick to the teaching, the lecturing, and one of your pet interests is teaching methods to graduates and undergraduates.
Yeah.
Can you just give us your opinion on the best way, if there is a best, or one of the best ways, one of the best ways?
It depends on the group of students you're teaching. If it's students who are studying, for example, the introductory course in maths for the economics degree-based programs.
Which would hold for our students.
Yes, so the Mathematics 1 program. The question there, or the difficulty there, and the question they might ask is, well, why do I need to know this mathematics? Because they may not immediately see the application or relevance of it. So one way in which we've tried to structure that course is to sort of convince them of the need for the maths before we deliver the maths. So we say, look, here's an economic problem, quite a simple economic problem, but how on earth can we begin to make any sense of this? How can we move towards understanding it or solving the question? We need some tools. Here are the tools, and then here's how we use them. If you just said, here's some interesting mathematics for mathematics' sake, they would inevitably question whether or not they should be interested, and that affects their approach to learning the stuff in the first place. So when we're teaching or designing courses for students in economics, we always have to, we don't have to overdo it, but we have to have in mind that you want to sort of hook them by saying, here's a problem in economics that we really want to answer, but we can't answer it. Here's some maths that will enable us to, and here's how that's used. So that it's motivating it in the first place, then doing the mathematics, and then showing how the mathematics is applied. I think those are the three things for each topic in the course that we try to do.
Okay, and another question about more UK students. When they come from their own levels in their A levels, what is the level that you get as starting material for your courses?
Right. I'm fortunate to teach at LSE where the entry is very competitive, and so the students that we get have really strong A-level results. But even there's a transitionary problem from school and A-levels to university-level mathematics, and every university in the UK experiences this. And it's because A-levels tend these days, anyway, to focus on applying standard techniques to standard problems. So the students have a repertoire toolkit of techniques that they know how to operate. But when they come to first year university level mathematics, you have to stop and breathe and begin to think about what these techniques mean and why they actually work. And these are questions that sometimes the students have never actually asked themselves. They're just applying these techniques without understanding why they work. So when you stop and ask why they work, you then have to start thinking about how you prove things abstractly in mathematics and how you even formulate formal statements. And this is a bit of a jump for most students, even the very best, because it's a completely different way of thinking. They're used to solving problems and performing calculations and techniques. And then you get them to university and you sort of say, what do we mean by a number? And more sort of theoretical abstract questions like this that they get in the end, but they struggle with initially.
But do you think there is a balance between the theory and the applied part for economics, investment management, those subjects?
They, in those degrees, would probably not spend much time at all on sort of the logic or philosophy behind mathematical proof. Again, for those students, maths is about a set of tools they need to solve particular problems. The students I teach, or many of the students I teach, are doing a combined program in maths and economics, which we also offer on the international programs. And for those students, they do get that balance between the sort of economics and finance courses and the, not just the methods courses in maths, but the abstract reasoning, theoretical courses, pure mathematics courses too. And actually, I think it does them well, because I'm a great believer in the effect that a maths a pure maths, a proof-based maths course can have on the way people think. Because if you spend a lot of time thinking about how to prove things, you can learn how to look at a problem and work out which bits of it are really important and central, which bits are just detail that doesn't matter. And so that way of thinking is very useful for students in later life, whether it be in further study or just in the job of work. I've often thought that heavily vocational study is not so useful, because if you learn a sort of set of tools and techniques and you take them into the workplace, they're probably out of date almost as soon as you walk in the door. And so that's not what you need. What you need is the ability to think and reason and not be, scared to do some analysis of problems that involves thinking about them slightly abstractly.
But one problem we see, everyone seems to have, and we mentioned it earlier on in the meeting a couple of days ago, is learning by rote.
Yeah.
Which means you're displacing, say, pattern, which we mentioned earlier on, the beauty of pattern.
Yeah, you're doing what if you learn by rote, you're doing what the statisticians call overfitting. So if you were trying to model, if you're trying to learn from data, just to get back to my researcher, if you're trying to learn from data, what you ideally want to do is find as simple an explanation as possible for the underlying patterns. Right? Now, if you simply learn each individual piece of data, there's no real learning going on there. You're just remembering the data as a table of data. You're not extracting generalities and the principles behind the data. Similarly, if a student simply looks at lots of previous questions and their answers and studies those and memorizes them, they might learn something from it, but they don't learn as much as if they sort of try to take a step back, try problems for themselves and realize what general principles they can draw from the examples they've seen and done, not just memorize. And the problem with memorization is that it doesn't necessarily help ultimately in an exam, because the questions are always going to be different anyway. Some of them will be similar in routine, but there's always going to be really surprising ones, deliberately so.
And now going to the public in general.
Yeah.
What is your opinion on the public's perception of any branch of mathematics? Let's just put the monster, that's why I call it the monster. It's a whole Pandora's box, so to speak.
Oh, several things here, I suppose I can say. I mean, one thing that, just think about the attitude in the UK anyway. General member of the public is probably slightly afraid or daunted by mathematicians. They sort of, they think, most of them, that it's an incredibly hard thing to be doing, and they always struggled with it at school, and that you must be some kind of unusual human being to be able to cope with this. I mean, that's not to say that they think you're weird, but they think that they're almost in awe of you for being able to do something that they see as so difficult. That's, I think, what many members of the public would think. Other members of the public might not be so in awe of mathematicians, but think that what we do is, sort of abstract, ivory towers, theoretical blue skies research that isn't actually very important. And they couldn't be more wrong, because as you know, a lot of the applications of maths were not envisaged in the least by those who did the original maths. G.H. Hardy, the famous Cambridge mathematician, said that he wasn't at all interested in applied maths, and he would be almost offended if his mathematics was regarded as applied mathematics. But yet he laid mathematical foundations that have been used in all sorts of applied areas of mathematics, and similarly with other mathematicians. The stuff that they do decades later suddenly becomes, one of the toolbox
That
techniques.
was the point I made earlier on. The pure mathematician just sitting on the beach, thinking, nice job.
Yeah. So I think there's a lot of people who think, we don't understand what we do, but we're in awe of you. And there's some other people who think, you're getting paid to do something that's largely self-indulgent.
But do you think that the press, this is just a general question, go back to Einstein, the work he did hit the press all over the world. Okay, maybe it's a different kind of work.
Yeah.
What about today? Do you think that there's soil for that?
I think there is still, I think the press is still generally positive about mathematical discoveries. I mean, there's often press articles about people cracking new cipher systems and things like this. the press was very excited, for example, though it's physics more than maths, about Higgs winning the Nobel Prize and things like this. The press is always, it always writes fairly positive articles about mathematical modelling in economics, for instance, especially when it results in Nobel Prizes. So I think the press is generally, positive about mathematics. I think, some members of the public might consider it a bit of a waste of time, but I think the press generally sees it as a worthwhile activity, even though they don't fully understand it. And any time they try to write anything with any detail, it's usually wrong. that's the way.
And one last comment, this is very general. The public sees, or some members of the public sees mathematicians as disorganized.
Yeah.
Go into their office and you see, I don't know what you see, a whole mess.
The absent-minded professor who's got absolutely no social skills whatsoever.
Is that,
Right?
is that
You know the old
true?
joke, how can you tell an extrovert mathematician? He looks at your shoes when he's talking to you. Well, the introvert mathematician doesn't even look in your direction. So,
Is there a true perception? Is that perception based on true fact? In your opinion?
in my opinion, in my experience as an undergraduate, I had some extremely strange mathematics lecturers, but I think it's not necessarily a fair opinion. I think it comes down to this sort of impression that mathematicians are doing stuff that is beyond normal human comprehension, and therefore, because of that, they must be just weird.
Yeah.
Mathematicians being messy, absent-minded. Yes, I think there is that impression.
So
I don't think it's justified, but I think there is that impression.
Thank you so much, Mr. Bush, for being with us today and for those very interesting questions. Thank you, Professor
My pleasure.
Martin, for, as Mr. Bush so aptly said, removing the fog from so many aspects of mathematics. Good evening from Aspire Magazine. Good evening from St. Martin's.